Now that we have some understanding of what discontinuities are and are starting to understand what continuity means, we want to get specific about how can we determine whether a function is continuous at a given point. Now, you might be thinking, well, just look at the graph, and if there's no holes or gaps or infinite asymptotes, then it's continuous. And to some extent, that's basically true. The trouble with that is if you don't have the graph, then you can't use the graph. Also, even looking at the graph, if we got really nitty-gritty, if we think about one like this, if that point discontinuity was drawn to scale, it would be infinitely small, right? A single point has no width at all. So even if that point was undefined, we wouldn't be able to tell unless we could zoom in infinitely close in onto it to be able to see it. If we use like a lot of graphing calculators or most graphing utilities, you won't be able to visually see a hole because it's infinitely small. So what we want to do is be able to identify algebraically whether a function is continuous at a particular point. And in order for that to happen, three things need to be true. So here's the big thing, the continuity test for a function at a given point C. A function is continuous at x equals c if it satisfies the following conditions. The function is defined at c. In other words, there is some function value that exists. So f of c exists, the function exists. The second criteria is the function approaches the same y value on the left side and on the right side. Okay, approaches the same value on the left and the right. This is heading toward limits, which we'll talk about later. So when we might even come back to this discussion on continuity later in the year. We may or may not get around to it, but that's going to be a key idea here, this idea that it's approaching the same y value on the left side and the right side. We'll talk about that in the examples. And then also that the y value that the function is approaching from part 2 is equal to the function value from part A. So this approaching value is equal to this function value. If a function is continuous on an interval, or excuse me, we would say a function is continuous on an interval if and only if it is continuous at every number x in the interval. So this test is determined at a point, and if it's continuous at all points on an interval, then we can say the function is continuous. So a couple of points for us to note. Linear and polynomial functions that we've been talking about, they're all continuous everywhere. You'll see later on that all of the functions that you've been studying all this year, the sine function and all these guys, the exponential functions, log functions, all of them are continuous everywhere on their domain. That's kind of what defines it as being its domain. And also important functions that aren't continuous everywhere include some of what we've been talking about, right? The piecewise functions are not continuous everywhere. Rational functions that we're about to start talking about have a lot of discontinuities. Okay, so it's important for us to identify where a function is and is not continuous. So let's go ahead and do some examples where we determine whether a function is continuous. Starting here with this first one, it says determine whether each function is continuous at the given x value. So what we just said is a test for determining whether a function is continuous at a point. And in order for that to be true, the function has to exist at that point. It has to approach the same y value from both sides of that point, and the value that it's approaching from both sides has to equal the function value. So let's walk through that piece by piece, steps 1, 2, and 3. 1, we need to determine whether the function value exists at that point. That's as simple as plugging in x into the function. So f of 1 equals 3 times 1 squared plus 7. That's 1 squared is 1 times 3 is 3 plus 7 is 10. F of 1 is 10, so the function does exist. Okay, check, done on that part. The second part is the weirder part that we're not used to. What we're going to do is figure out what are the y values going toward as x gets close to 1. So we want to think about as x approaches 1. Sorry, I didn't write that right. As x approaches 1, what does f do? Or what does the y coordinate do? What does f of x approach? So what we're going to do is just make a table here. I'm going to make a table of x values that are getting close to 1 and find the corresponding y values and see if they're going towards some specific number. So as x gets close to 1, it could be coming toward 1 from below 1. So a number that's close to 1 but not quite there might be 0.9. And as I get closer to 1, maybe I'd be at 0.99. And then maybe I get a little bit closer still. I'm at 0.999. And this is a really typical pattern. You maybe start about a tenth of a unit away from the number you're approaching and get down to 100th, down to 1,000th. And we want to get really, really close. So we're trying to see what is the y value going to go toward as my x value gets really, really close to 1, but not quite to 1. We know it's equal to at 1. We're trying to get close to 1. So now we just need to evaluate these function values so we can plug them all in to that function. It's a bit tedious here to plug 0.9 into that function, so I would definitely suggest using your calculator. So I have used my calculator. I've stored that function in here already. You could type each function value in manually. It might take a while. You could use a Microsoft or an Excel spreadsheet to do that. Or if you have a graphing calculator, you can program the function in to do this repetitive substitution here. But this is going to allow me to evaluate f at 0.9 and see that it's 9.43. Now I need to do f at 0.99. So I can do f at 0.99. I get 9.94. Then I can do f at 0.999. I get 9.994. And you might be catching on to a pattern here. It certainly looks that as x goes toward 1, that f of x is going toward, hopefully it's clear that it's going toward 10. Okay, that's true on the left. So on the left, as x goes toward 1, y goes toward 10. What I mean by left is below 1, to the left of 1 on the number line. We also need to do it from the right. We have to do it from both sides. So we have to think about from the left and from the right. We have to do both. So now I want to think about x values that are close to 1 but above it. So maybe 1.1, then 1.01, 1.001, and keep getting close to 1, closer and closer to 1, and do the same substitutions here. So I'd have f of 1.1 equals 10.63. Then I can do f of 1.01 equals 10.06. And already we can see where this is going. F at 1.001 would equal 10.006. And it looks like pretty clearly that in the same way as x goes toward 1, f of x is going toward 10, but just from above. So in both cases, as x goes toward 1, f of x goes toward the same value of 10. And now we're ready to go ahead and say that these are continuous by doing our third step. The third step says the y value that the function approaches is equal to the function value. So we need to go ahead and say that. F of x approaches 10 as x goes toward 1. And that is equal to the function value at 1. Therefore, we can say f of x is in fact continuous at x equals 1. And that's our conclusion. Now, it takes a while to walk through that the first time. As you get more and more comfortable making that table and using your calculator, you'll start to see that this can go a lot quicker. So I would encourage you to practice using your calculator or Excel or some means of generating those function values more quickly. But those are the 3 steps that are essential to showing that a function is continuous at a given point. That the function value exists, that as x goes toward the value you're interested in, the function value goes towards some specific number on both sides, and that specific number is equal to the function value. Then you can say that the function is continuous at that point. In the next video, we'll just practice doing it on a couple more examples here, and keep practicing getting a better understanding of how to determine continuity.